Hello again, welcome to my science channel. We're going to have like a power factor tonight, and throughout the video we'll be picking up many important issues with power factor, and a lot of it involves the magnetic fields building up around wound components on AC. You only get it on AC, you don't get power factor problems on DC. Now, you can have lagging and leading power factors, which is something we'll have a look at in a minute, depending on if the load is capacitive or inductive. And it develops from wound components like motors and transformers where they use coils, and it's the forming of the magnetic field around these components. But of course, as the mains signal rises and diminishes, so does the magnetic field. And the magnetic fields collapse, then you have a back EMF, which is essentially fighting against the source voltage. And with capacitive loads, you have energy taken up in the formation of the electric field across the dielectric of the capacitor. So you've got two things here which are using up power. So it's the magnetizing field around coils and the electric field in the dielectric of the capacitor. So first of all, what we'll do is we'll have a look at our main supply to see what that looks like, and then from there we're going to develop that and have a look what the supply looks like across reactive components such as inductors and capacitors, and then from there develop where power factor comes from. So we're having a look at the main supply now. We've got an oscilloscope, and what we're going to do is put a 50 Hertz signal onto this. Now if you looked at a 50 Hertz signal in real time, you won't be able to see anything because it's changing 50 times a second. But with the oscilloscope, what that enables us to do is to freeze the sine waves in time. So let's have a look what a 50 Hertz signal looks like. So that's our 50 Hertz supply signal. And what you can see is the signal raises, it and drops, then reverses in direction and goes back to zero. The height of the wave is called the amplitude, and so that'll be 230 volts to there and negative 230 volts. So that'll be positive 230 volts to there, and from there, and then from there to there is negative 230 volts. So we can see the sinusoidal wave of the main signal and how it reverses. Yeah. So we've got our positive 230 volts up there, comes down, reverses, and negative 230 volts there. Now that's the mains sinusoidal supply. If we could freeze it in time, that's what it would look like. So what we're going to do from here now is we can have a look at what happens to voltages if we put them across a resistor and a coil, and then we develop our power factor from there. So if we first of all take a look at a resistive load, so if we've got an AC signal here and that's going across a resistor, and we think about the current and the voltage, well, we can say that the current and voltage are actually in phase with each other. So if we drew a phasor, the current and voltage would be in phase with a resistive circuit. Now we can have a look at the graph of current against voltage for that, and it looks like this. So this is the graph of the resistive load. Our voltage in the circuit is green and our current is red. So as we can see, as the sine wave builds and then falls away and then reverses, the current is in phase with it. So it starts, peaks, finishes, reverses, peaks, and goes back to zero all at the same time. So now if we look at an inductive load, so that's like a coil of wire. Now remember, we've got magnetic field surrounding that, and the energy returned to the circuit from the collapse of the magnetic field causes the current to lag the voltage. So we can say, if we draw a phasor for the voltage there, and this is an ideal scenario where the current will lag the voltage by 90 degrees. If we look at the graph of that, we can see this. So with the graph of the inductive load, we can see your voltage there, still in the same place, it's a reference, but here we can see the current is actually peaking and then going back to zero and reversing after the voltage. So the current is lagging the voltage. So if we now look at a capacitive circuit, we know that there's going to be power taken up in making the electric field, and the electric field is going to discharge back into the circuit when the sine wave diminishes. So now the effect that this has on the supply is, once again, if we use the voltage as a reference, V, and we can say in a capacitive circuit that the current is going to lead the voltage by 90 degrees. And if we now have a look at the graph of that, then it looks like this. So with our capacitive load, we can see once again the voltage in the same place, but now our current is peaking before the voltage peaks. And you can see it in the reverse direction as here, peaking before the voltage peaks. So the current is leading the voltage in a capacitive circuit. So if we take these factors into account now, we can see that our voltages and our currents are being moved around a little bit in the circuit. As we said, that in an inductive circuit the current lags the voltage, and in a capacitive circuit the current leads the voltage. So this gives us three different powers that we can talk about now. We can talk about a true power, an apparent power, and a reactive power. And they're very, very important and are called the power triangle, which looks like this. So if you look at the power triangle here, what we can see is the apparent power, and that's calculated, that's called S, and that's calculated by V times I, voltage times current, and that's measured in VA. So the units is VA, and we're all familiar with the units kVA and things like that, which is thousands of VAs. The reactive power here, now that's the power that is used in making the magnetic field around the inductive component, and that's called the reactive power. And if we wanted to calculate that, we call it Q, the reactive power, is equal to the voltage times the current times the sine of the angle there, angle phi. And the true power of the circuit is power is equal to V times the current times the cosine of the angle there between the apparent power and the true power, and that's measured in watts. And incidentally, reactive power is measured in var, true power is measured in watts, and apparent is VA. So the true power is the usable power, the apparent power is the power that's apparent in the circuit, and the reactive power is the power that's used up in the magnetic fields. And we want to try and get that as small as we can. So that's the power triangle. But what we can do is use what's called the beer analogy to clarify this. And this will make these things a bit more clear. So this is a glass of beer model for our true, apparent and reactive powers. So here's your reactive power. That's the power taken up in making the magnetic fields around the coils, the field expanding and collapsing, expanding and collapsing. So that's that power. You've got the true power is the beer, so that's the actual usable bit, and you've got the apparent power, which is both the foam, the head of the beer, and the actual beer itself. So you've got the apparent power, which is all of it, the reactive power, which is just the useless foam on the top, and the true power, the actual beer in the glass. This is the power you were using to drive your machine. What we've seen now is we've looked at the power triangle, and we said the power factor is the angle there between the true and apparent, or the cosine of that angle, cos phi. So we said power factor is cos phi, but power factor is also the true power divided by the apparent, and the proper definition of it is the ratio between true and apparent power. So to have a closer look at the maths in this, what we've said is if the current and the voltage are out of phase by an angle phi, that angle is the power factor. And similarly, we talk about apparent power and true power. and it's the same. So we've got the apparent power there, and the true or real power, as it's known as well there. And then the cosine of that angle phi there is once again the power factor. And if we look at this, this is just basic trigonometry, because if we look at that trigonometrically, we could say cos phi, if you remember SOHCAHTOA, is equal to the adjacent over the hypotenuse, which is that. So power factor is the apparent, is the true over apparent, true being the adjacent and apparent being the hypotenuse. So if we have a look at some scenarios that we're going to experiment with a little later on, what we could say then, if we had a power factor of 0.8, now bearing in mind that's the ratio, so if we say the inverse cos of 0.8 or the cos to the minus 1 of 0.8, we will find that equals 36.86 degrees. So that means that the angle between the apparent and the true is going to be 36.86 degrees. And then if we went to a power factor of 0.4, then cos to the minus 1 of 0.4 is going to be equal, if you tap this into your calculator, just the inverse cos, is going to be 66.42 degrees. So we've now got a larger angle between them. It's not quite the scale obviously, but that phi angle there now is 66.42 degrees. So as the power factor gets worse, we can see the angle there getting worse, and consequently the reactive power will get worse as well. So we need to put in power factor correction capacitors to correct that. How does this affect our circuit? We can say then that power in a circuit, power is equal to V times I times the cosine of phi. Well, that cosine of phi is your power factor, and that's a unitless number. It will just give you a number, for example 0.8. So let's have a look at the actual effect it gives us in our circuit. So we're going to have a look at a load of 3 kilowatts at 230 volts, and we want to calculate the current at unity. Now when we say unity power factor, that's when the current and the voltage are in phase. We'll look at it at a power factor of 0.8, and we'll have a look at it at a power factor 0.4. So first of all, if we wanted to calculate the current, we have to transpose the formula. Now voltage and cos phi are held to the current by multiplication signs. So what we need to do is divide both sides by these, which will give us I, current, is equal to power divided by V cos phi. So if we put some figures in, I is going to be equal, now we've said it's 3 kilowatts, so that's 3,000. 3,000 divided by 230. First of all, at unity, which is, so it's a power factor of 1, so 230 times 1. So I is going to equal 3,000 over 230, and that's going to be 13.04 amps. Okay, all well and good. So for our second one, it's at 0.8. So if we do this again, so I is now going to be 3,000 over 230 times 0.8. So we can see our bottom line is changing now. So the current I, if we work that out, 3000 divided by 230 times 0.8 is 184. So that will give me a current of 16.30 amps. So we can see already now that with the changing in the power factor, for the same power, 3 kilowatts, the current has gone up from 13.04 to 16.30. So let's have a look at our last scenario of it being 0.4. So that's 3000 divided by 230 times 0.4. That'll give me I is equal to 3000 divided by 92. 92, and that will give me a current of, change pens, 32.6 amps. So what you can see from these three different scenarios, the power you take in is the same, 3 kilowatts. The power factor, possibly because a power factor correction capacitor has failed or something like that, the current has increased with a decrease in power factor. So I kind of answered the question a little bit there, as well as how do we correct a poor power factor. Now we know that the power factor lags with an inductive circuit and a power factor leads with a capacitive circuit. So what we have to do is put in power factor correction capacitors. Now these capacitors can either go in at the service intake position, where you can have capacitor banks. Sometimes they can be switched in and out by relays depending on the load as well. Or you can connect them locally. So if you think about fluorescent lighting, it's got a power factor capacitor connected in with it. Also motors and things like that. You can have the power factor capacitor connected at the motor terminals. So you can see it's very important, because with a poor power factor, it's taking 32.6 amps, and we've got to build the cables, or the cables will have to be sized to take that current. But why do that when you can have much smaller cables to take the 13.4 amps, giving you the same power there? So it saves you a lot of money in power, because you're paying for this, so you'd be paying for less energy consumed, and also your infrastructure can be downsized to calculate the smaller to carry the smaller current for the same load of 3 kilowatts. So I hope you found that little talk on power factor interesting and useful for your studies now. And if you want me to cover anything, please put in the comments, and please like and subscribe. Thank you very much for that, and stay safe.